Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this problem, we're asked to compare the currents between two loops of wire that have different shapes but experience a lot of the same circumstances when it comes to torque caused by a magnetic field. So what we're going to do is we are going to analyze what it means for the surface area of each of these coils because they're made into different shapes. And then we're going to compare the expressions for the torque between the two in order to compare the currents. So what we're given is we're given two lengths of wire. They both have the same length, and we'll call it big L. Now, it's fashioned into two different coils, but both with just one single turn. One of the wires is made into a square. So we're going to take that long piece of wire, fashion into a square, right? And we'll say that each side is little l. Now, that means that to relate the total length of the wire with with each side of the square, that means the total length can be expressed as 4 times every individual side of the square. Good to know. Now, the cross-sectional area of this one-turn square loop is, of course, going to be L squared. Now, up here, we have an expression for little l, one side of the square, in terms of big L, the whole perimeter or length of the square. And we're going to write that in here. So we solve this for L. L is going to actually be, let me write this here. Little l is going to be the total length, O divided by 4. So we plug that in here, L over 4, square the whole thing. We see that the surface area, the cross-sectional area, of our square loop is given by the total length of the wire that makes that loop divided by 16. Square that length and divide it by 16. Now, the other piece of wire is made into a circle instead, right? And so we know that the total circumference of the circle must be the same as the length of the wire that made the circle, and that's going to be equal to 2 pi r, relating that to the radius of this circle. Of course, then r can be expressed as the length of the circle divided by 2 pi. Now, we're going to then want to express the cross-sectional area of our wire, of our circle for this piece of wire is going to be pi r squared, of course, because that is the cross-sectional area of a circle. Plug our new expression for r in here, L over 2 pi, and we will square it. And we see that the area, cross-sectional area of the circle, in terms of the circumference of the circle or the length of our wire, is given by L squared over 4 pi. Now, the nice thing about this problem is that the two situations we have the two different loops in the same magnetic field at the same orientation experiencing the same torque. So we have the same magnetic field, the same orientation, the same torque experienced, and we're trying to find the ratio of the currents flowing through the square divided by, the currents of the ratio of the currents flowing through the square loop to the circular loop. So we want to find that ratio. But we know how to express the torques that these are experiencing in terms of characteristics of the situation in the loops themselves. And we're also told that the torques they experience are the same. So the expression for the torque on the square loop should be the same as the expression on the torque for the circular loop. So let's write those out. What is the expression for the torque acting on the square loop? Well, of course, it's going to be the current going through the square loop. The number of turns, which is 1, times the number of the current through the square loop, times the cross-sectional area of the square loop, multiplied by the magnetic field that the square loop is in, multiplied by sine of the orientation between the square loop and the magnetic field. Now, that's got to be equal to the torque on the circular loop, which is going to be the current through the circular loop, multiplied by the cross-sectional area of the circular loop, multiplied by the magnetic field that the circular loop is in, multiplied by sine of the orientation angle between the area and the magnetic field. Now, a lot of you see that the magnetic field term and the orientation term, of course, are the same for each of these. So they cancel out. We can divide them out on each side of of the equation. So what we see is an expression of the current through the square loop multiplied by the cross-sectional area of the square loop is equal to the current through the circular loop multiplied by the cross-sectional area of the circular loop. And you see from here we can solve for the quantity we're asked to find. The ratio of the square loop's current divided by the circular loop's current. Now, if I rearrange this equation here and solve for that ratio, we see that it's equal to the ratio of the cross-sectional area of the circle to the cross-sectional area of the square. Now, we know our expressions for that, though. The cross-sectional area of the circle is given by L squared divided by 4 pi, and we have to divide that by the cross-sectional area of the square, which is given by L squared divided by 16, right? We can divide these, flipping the reciprocal, L squared over 4 pi multiplied by 16 over L squared. We see the L squareds cancel, and this ratio is actually simply 16 divided by 4 pi, or 4 divided by pi. Now, since 4 is 1 more than 3, and pi is just a little more than 3, this is going to be a ratio that's a little bit more than 1, right? So we see in the end that the ratio between the current in the square loop to the current in the circular loop is given by 4 divided by pi, which is about 1.27. And that is our answer.